So in case things started getting a little confusing last time, uh, today we're starting a new topic, so it should be much easier, less prerequisites. Um, the the questions today involve the concept of elementary embeddings, and I thought I should be a little clearer. I mean, often in the talks I've been giving, I've been saying things like there is an elementary embedding J from V to M. And in general, this is not a first order quantifier here because J is a proper class. And usually in set theory, especially ZFC large cardinal theory, this is explained away by saying, well, all the elementary embeddings that I'm interested in are just definable from some parameter. So really what I'm saying is there is a parameter that from which one can define an elementary embedding. Which is still somewhat problematic because definability is not first order, really. So, but often, usually the definition is pretty simple. So you can say something like, there is a parameter from which one can define it by a sigma 2 formula, an elementary embedding from V into some inner model M. And this is now actually first order statement in the language of set theory. And every embedding that comes up in ZFC large cardinals seems, at least almost all the important cases, you can get by with this kind of statement. But we'll see today that that's not always possible. Oh, there's yet another problem which I think is worth explaining if you haven't seen that explanation before. Elementary says that the embedding preserves all first order truths, but that is again problematic because the satisfaction predicate for first order statements is not definable. So how can you say that this parameter defines an elementary embedding? Say, even if you have a fixed formula phi, you could, it's not clear that it's a first order statement to say that the set of all A, or the class of all A, B, such that phi of A, B will be is an elementary embedding. It's not clear that this is first order. So is an elementary embedding, I guess. You can say from V to some model M. So there are numerous problems, logical problems that are showing up here. So first, how do you say elementary? And then what is this M? It seems like there's another class I'm quantifying over. But actually, it's easy to find M. If I want to tell you that this class is an elementary embedding from V into some structure M, there's really only one possible choice for M, at least if we want M to be transitive. The obvious choice is that we could say that this class A, B, such that A, B, and P hold is an elementary embedding. This is what you would want to be true from V into this union of all the sets, let's call them N, such that there exists an alpha with V holding of V alpha with N and P. So this is really trying to say the union of all, if this defines an elementary embedding J, this would be the union of all the J of V alphas for alpha in the ordinals. Okay, so this is the only option for what the target model of the embedding can be. If you have an elementary embedding whose domain is V, its codomain must be the union of J on the V alphas. It's the only place to which B could be elementary embedded by some map. So so this statement, if we're worried about formalizing the statement that some formula and some parameter define an elementary embedding, the issue is not about the target model here. I hope this is not too confusing. Can anyone, if what I'm saying is confusing right now, can someone raise their hand and say I am confused? And if not, then I'll assume that I'm not confusing you. Okay. Okay, so what I'm saying is perfectly clear. That's great news. Okay. So there is this issue of whether the embedding is elementary. And the standard way to take care of this in set theory is to note this great fact. So if J from M to N is cofinal and sigma 0 elementary, and M and M are models of ZF. Actually, I think it's only relevant that M is a model of ZF. Then J is actually fully elementary. So you can, if M and N are proper classes, then this fact is again not a first order statement in the language of set theory, but you can think of it as a scheme that says, you know, this part is first order, cofinal and sigma 0 elementary. So the scheme is saying that for any formula, any fixed formula, you can actually prove by induction, assuming just this, that J preserves that formula. So that's what I mean by fully elementary. It's stated schematically. So if I want to say that this is an elementary embedding, all I really need to say is that it's a sigma 0 elementary embedding, since V is assumed schematically to be a model of ZF. So this M satisfies ZF, again, in the case that M is a class. You can't really say that M satisfies ZF. but yeah, so I'm going to assume that you are familiar with the way of getting around that problem at least, which is to say that, well, if M is going to be a proper class model containing the ordinals, M satisfies ZF if and only if M is almost universal and closed under the Gödel operations. This is the basic. I don't know. You can read that proof in Yek's book or Mori's book. But anyway, so all these things that look so like profoundly second order really reduced to first order statements, at least except perhaps for the definability of the embeddings that you're interested in. So at least once you're given a class, it's a first order statement with reference to that class as a predicate to ask whether that is an elementary embedding from V into some model M. So you can recover the model M just by looking at this union. Maybe did I erase it? And you can recover, and you can talk about elementarity because all you need to know is that the embedding is cofinal and sigma zero elementary. Okay, but we're actually in a situation where the definability of embeddings becomes an interesting question. So Suzuki proved this theorem. So this is after the proof of the Kunin inconsistency theorem that there is no J from V to V. Suzuki proved, working only in ZF, that there is no definable J from V to V. Obviously, I mean, there's no definable elementary embedding J from V to V, except for the identity. The identity is definable. So how do you do this? So I'm sorry about all the meta math. I thought it would make things clearer if I really tried to explain what's going on meta theoretically. Again, if you look at this theorem, this is not a first order statement, even though, so the way to think about it is it says for each formula phi does not define an elementary embedding from V to V, except if phi defines the identity. But the point here that I'm making is saying no, definable is not something you can express with a single formula. So instead, this becomes infinitely many theorems. So this is a theorem scheme. Okay, so with that in mind, the proof starts by saying, well, fix a formula phi that, so, and this is definable from parameters even, because typically the embeddings you look at in set theory are only definable given a parameter. So fix a formula phi that purports to define an elementary embedding. So that means that J should be equal to the class of pairs A, B, such that phi holds of A, B, P. Right? This is how formulas can define functions. Okay. So let's say that for each Q, we can actually try to define a different function. We'll let JQ be equal to the class of all A, B, such that phi holds of A, B, Q. So we can look, so for some Q, J sub Q might actually successfully define an elementary embedding from V to V. So let's C be the class of all the parameters Q, such that JQ actually is an elementary embedding, non-identity. From V to itself. And let's let kappa be the minimum critical point of JQ for Q and C. So now the issue is that kappa is a definable ordinal. I just defined it because C is a definable class. C is just defined using this formula phi, and the fact that we can say elementary embedding by just using this definable property, the property of being sigma 0 elementary and cofinal. So the sigma 0 satisfaction is first order definable. So you can define C and you can define this ordinal kappa. But now if you take Q, witnessing that kappa is this minimum ordinal, so let's take a Q such that Q is an element of C, so JQ is elementary, and we can have the critical point of JQ be equal to kappa, because kappa is this minimum ordinal. It's the critical point of such a JQ. Then we have that JQ of kappa is different from kappa. But that's a contradiction because kappa is definable in this structure V. It's definable without any parameters. So kappa has to be fixed by any elementary embedding from V to V because it has to be moved to the ordinal defined by exactly the same formula that kappa was defined by in V. So this fact is a contradiction. So there can be no definable from parameters embedding from V to V. And if you think about it, that's not such a surprising fact. These embeddings, once you start looking at them, they have to be incredibly complicated. And their complexity doesn't ever diminish as they go up. That an embedding from V to V, and in normal large cardinal theory, as the embeddings get more and more resemblance between V and their target model, the complexity of the parameter that you need to define the embedding grows and grows. So it's not really that surprising that that once you're at the level of embeddings where the target model resembles V to the maximal extent, those embeddings are not definable from some set parameter. So the complexity of parameters required to define embeddings with great resemblance, typically it seems to grow as the resemblance increases. But it is worth noting this is a ZF fact. I never use the axiom of choice here. So it's quite different from Kunin's theorem. You saw, by the way, a proof of Kunin's theorem last time. I should remind you, I showed you the wooden proof of the Kunin inconsistency theorem. And that, it didn't just, this rules out definable embeddings, that ruled out an arbitrary embedding. So you should think about how would you even formalize the difference between those two theorems. And one way to do it is, so the Kunin inconsistency theorem formally states that it's not stated in first order set theory. It's a truly second order fact. Think of it that way. It says there is no elementary embedding from V to V and this quantifier really is intended to be interpreted as a second order quantifier. So we're working in second order set theory or class theory. If you want to read about class theories, the most elegant one is called von Neumann, Gödel, Bernays. I don't know, for some reason I always want to call it NBG. Some people call it NGB or GNB. It just depends on, you know, your total ordering, on your preference between these three people. But in any case, this is the class theory I'll work in. It's a conservative extension ZF. So a lot of formalizations of this include some version of the axiom of choice. For example, you can even say things like, there's a choice function that acts on every non-empty set. But I'm not, when I talk about NBG, if I ever have to talk about it again, I'll only be talking about the choiceless version of this. So no version of the axiom of choice whatsoever. So if you've seen this before, typically the way that you prove that this is a conservative extension of ZF is you start with a model of ZF and you expand it by adding, so that this theory has two sorts. It has sets and classes. And to find a model of NBG, you can start with a model that just has sets, like a first order model of ZF, and add for the classes just all the definable from parameters subsets of the model. And that will give you a model of NBG. But the models of, not every model of NBG has to look like that. There are models of NBG that also have undefinable classes. So just because the conservativity proof uses this construction that only involves definable classes doesn't mean this theory says requires that all the classes are definable. So in this theory, we can actually quantify and say there is an elementary embedding from V to V, and that requires always that if you have any model of that theory, that means that that model does have an undefinable class in it, because that's exactly what Suzuki's theorem is telling you. Okay, so anyway, yeah, so the Kunin inconsistency theorem, you can talk about class theory. Another way to think about it, though, is there are first order consequences of the existence of a J from V to V, many of them, and you can actually, Kunin's theorem actually shows you how to refute those first order consequences in ZFC. So for example, I briefly defined in the first talk a rank Berkeley cardinal. And I think this is a sort of elegant way of getting around what seem to be all these metamathematical issues. You don't, it's good to understand what's going on metamathematically, but you can actually get away without worrying about it at all just by moving into a first order context. So a cardinal lambda is rank Berkeley. If for all alpha less than lambda and all beta greater than or equal to lambda, there is an elementary embedding from V beta to V beta such that the critical point of J is between alpha and lambda. So this was introduced by farmer Schlutzenberg, who noticed that if you have an elementary embedding J from V to V, well, in Suzuki's theorem, the big problem with these embeddings was that their critical points can never be definable. Their critical points sort of, and that means that even though the critical points of embeddings are sort of how we get large cardinals out of embeddings in ZFC, the critical point of a J from V to V doesn't actually have any, it's not a specific key point with respect to the other sets because it's not definable at all within set theory. On the other hand, the kappa omega of J conceivably could be a definable point. And kappa omega of J, for example, is always a rank Berkeley cardinal. So how do you prove this? So it's kind of a cute trick. So what you can do is say, so remember how kappa omega of J is defined. So kappa omega of J is equal to the supremum of the kappa n of J's. And this was equal to, kappa n of J was equal to J of J of J of kappa. So n times. So kappa n of J is the first fixed point of J above its critical point. So the way to prove that this ordinal is a rank Berkeley cardinal, well, it's not totally obvious just from the fact that you have a J from V to V. And the problem is that a J from V to V, it's not going to fix every ordinal above kappa omega of J. So it's not just like you can say, well, kappa omega is a rank Berkeley cardinal because for any alpha, if I want my, for any beta above kappa omega, if I want my J from V beta to V beta, well, I'll just restrict my J from V to V down to V beta. That doesn't work because J of beta might be different from beta. So the obvious example here is that J of kappa omega plus kappa 0 is going to be kappa omega plus kappa 1. So you don't get J from you don't get an embedding, say I from V kappa omega plus kappa 0 to V kappa omega plus kappa 0 by restricting J. So what do you do? So we want to prove that kappa omega is rank Berkeley. The way to do it is to, well, one way to do it is by contradiction. So let alpha less than kappa omega less than or equal to beta be the least pair of ordinals such that there is no elementary embedding I from V beta to V beta with critical point of I in the interval alpha kappa omega. So towards a contradiction, assume that alpha and beta are the least pair with this property. So you have to be a little careful, I guess, about what you mean by the least pair. But there's just take any well ordering you want of the pairs of ordinals, the Gödel order, if you prefer. And then so this is, so we're doing a proof by contradiction here. So we're assuming that kappa omega is not rank Berkeley, and we'll prove that it actually is. Or we'll get a contradiction. And how do you get a contradiction here? Well, now you can actually just use J. The point is, since alpha and beta are definable from kappa omega, and J from V to V fixes kappa omega, J has to also fix alpha and beta. So that means that we can restrict J to an elementary embedding from V beta to V beta. That gives us I from V beta to V beta. And we know that I of alpha is equal to alpha. And now, if we want a contradiction, all we need to know is that the critical point of I is greater than alpha. So why is this? The point is that kappa omega is the least fixed point of J, and hence I, since I is just the restriction of J, above the critical point of J. So remember, the critical point of I is equal to the critical point of J because I is the restriction of J, so it's just kappa. So all we're trying to prove is that kappa is greater than alpha, but we know that alpha is strictly less than kappa omega. The kappa omega is the least fixed point of J above kappa. So alpha, since alpha is fixed by I and hence by J, alpha cannot be above kappa because otherwise it would contradict the minimality of kappa omega. So the fact that I fixes alpha, so this is J of alpha equal to I of alpha, implies since J of alpha is equal to alpha, we have that alpha is less than critical point of J, which is equal to kappa. So that means that this I contradicts the definition of alpha and beta here, right? Because we said by definition, alpha and beta are the least such that there is no such I. We just found I. Okay, so that gives us a proof of this this fact that the kappa omega of any elementary embedding is a rank Berkeley cardinal. So another way to think about Kunin's theorem is that it states just in ZF now that there are no rank Berkeley cardinals. And in fact, the reason is that there is no ordinal lambda such that there is an embedding from V lambda plus 2 to V lambda plus 2. But another thing that we could do is working in ZF, try to understand what's going on with Suzuki's theorem in terms of the definability of embeddings of levels of V to themselves, so the kind of embeddings you get from rank Berkeley cardinals. And the first interesting case here is the definability of embeddings from V lambda plus 1 to V lambda plus 1. So this is, we could still be, these are the kinds of embeddings on the brink of inconsistency with ZFC. So these have been studied since the 1970s. So lambda is a limit ordinal. This is the context. So if you have an elementary embedding J from V lambda plus 1 to V lambda plus 1, it turns out that J is definable over V lambda plus 1 from parameters. In fact, the parameter that you look at is J restricted to V lambda. So how does that work? The point is that J restricted to V lambda let's call that I. So if you want to figure out what is J for some X in V lambda plus 1, what is J of X? Well, J of X has to be equal to the union for alpha less than lambda. Well, it's J of the union for alpha less than lambda of X intersect V alpha. Right, because any element of V lambda plus 1 can be written as the union of all its fragments as alpha increases up to lambda. So the point is, X is a subset of V lambda, and V lambda is equal to the union of the V alphas. So X is equal to the union of all these fragments of X. And each of these, X intersect V alpha, is a subset of V alpha. So this is in V alpha plus 1. So it's in V lambda. So this is equal to the union for alpha less than lambda of J of X intersect V alpha. And this is equal to the union of alpha less than lambda of I of X intersect V alpha, because I already tells you what J does to elements of V lambda. Okay, so that lets you define J on any element of V lambda plus 1 just using I, the restriction of J to V lambda. So that tells you that J was definable actually in this structure v lambda plus 1, if you think about it, using just this parameter, restriction of j to v lambda. And if you think about this parameter, well, this is a function from v lambda to v lambda, but really it's, if you want to think about it as a set, it's the graph of a function from v lambda to v lambda. And that is just a subset of v lambda, since v lambda is closed under pairing. And so this parameter I is really an element of v lambda plus 1. So this shows this fact. Any embedding from v lambda plus 1 to v lambda plus 1 is definable over v lambda plus 1 from parameters in v lambda plus 1. Slightly surprising when you first see it, because these seem like complicated things, and we have exactly the opposite kind of result for embeddings from v to v. And even we know that embeddings from v lambda to v lambda can never be definable over v lambda. That's good exercise. So this is in the case where lambda is a limit ordinal. Of course, it's not true in the case of an arbitrary ordinal, because I just told you that for a successor of a limit ordinal, the opposite thing holds. So the theorem that I want to talk about today, it answers the question, what happens for an arbitrary ordinal? So it's a bit more complicated, but Farmer Schlutzenberg had shown if I is an embedding from v lambda plus 2 to v lambda plus 2, where lambda is a limit ordinal, then I is not definable over v lambda plus 2, or parameters in v lambda plus 2. And he asked, what about v lambda plus 3, v lambda plus 4? So the theorem is that if lambda is a limit ordinal, so this is due to me and Farmer, lambda is a limit ordinal, an elementary embedding j from v lambda, and n, I guess I should say, is a natural number. J from v lambda plus n to v lambda plus n is definable over v lambda plus n from parameters if and only if n is odd. So as I mentioned, sort of weird thing to have this periodicity feature of the power set operation. It's a property, a first order property of v lambda plus n, essentially, that these embeddings are definable from parameters, and it varies according to the parity of the level of the cumulative hierarchy you're looking at. And what's interesting here is that we actually have, if there's a rank Berkeley cardinal, then for all sufficiently large alpha, these non-trivial embeddings actually exist. So it's not a vacuous periodicity theorem. Actually, we have this periodicity and it's going on at all sufficiently large levels of the cumulative hierarchy. And it also it explains and refines Suzuki's theorem, because of course you can't have a J from V to V be definable, because even its restrictions to the levels of the cumulative hierarchy that it fixes, as long as they're even, are not definable. So it gets rid of sort of the metamathematics in Suzuki's theorem by refining it to just a first order fact, sort of the way the Kunin inconsistency theorem gets rid of the metamathematics in the second order formulation of the Kunin inconsistency theorem by showing that in fact you can't have an embedding from V lambda plus 2 to V lambda plus 2 in CFC. So let's see, how much time do I have? Can I hold a break early so that I can prepare to give the proof of this theorem?
Okay, of course. Sure.
Okay, great. All right, so yeah. Are there any questions about what I've said so far?
So your proof is in ZF, right?
Is what?
It's in ZF, not in AFC.
Oh yeah. I should always be saying, because I'm sort of switching theories all over the place. Yeah, this is a ZF, yeah. Because otherwise, there are only two cases, right? I already showed you the situation in ZFC, because the only possible embeddings in ZFC either go from V lambda to V lambda, where lambda is a limit, or from V lambda plus 1 to V lambda plus 1. And so, yeah, there aren't so many cases for this periodicity to take hold, but here, there's actually something going on.
So shall we take break now, right?
Yeah.
Okay.
And I guess come back around 15.
1850.
Oh yeah, so 15. Okay, it's fine with me. Okay, so what I want to show you is first how to, yeah.
Okay. You should share your screen.
Oh, good idea.
Yeah, that's great.
Yeah. Been in a class before where I started talking and they let me go for like 5 or 10 minutes before they told me that I didn't have my screen shared. So I appreciate how quickly you warned me. So what I want to show you is, remember, it's this theorem that J from V alpha to V alpha is definable over V alpha if and only if alpha is odd. So from parameters. But I'll give a partial proof. Somehow gets confusing to me if I try to prove this too abstractly, because I don't know, the limit cases are still slightly different even from the even cases. So it's easier for me to just think about a specific case, even though actually you'll see in the end, you can kind of just change the, in the end, the proof will look the same, whatever case you're in, but it's still easier to think about. So, so I'm gonna wanna assume that lambda is a limit ordinal. And I'll show you why if we have a j from v lambda plus 3 to v lambda plus 3, then j is definable over v lambda plus 3 from j restricted to v lambda plus 2. Okay, there's something to note here. Before when I said j from v lambda plus 1 to v lambda plus 1 is always definable from j restricted to v lambda. Well, j restricted to v lambda is actually an element of v lambda plus 1. So this has to do with how you do the set theoretic coding of functions. But technically, j restricted to v lambda is equal to the set of all a comma b. So the pair a, b such that b is equal to j of a, and b are in v lambda. And since v lambda is, because since lambda is a limit ordinal, v lambda squared is contained in v lambda. So j restricted to v lambda, which is a subset of v lambda squared, is a subset of v lambda, or in other words, in v lambda plus 1. But unfortunately, at successor ordinals, we're not so lucky. So a function from v lambda plus, or v alpha plus 1 to v alpha plus 1 is never an element of v lambda plus 2, v alpha plus 2. So the problem is that a pair of elements of v alpha plus 1 under the standard coding of pairs is not an element of v alpha plus 1. So now I feel bad because I started out by talking about definable embeddings and all this meta mathematics, and now I'm talking about how you code ordered pairs, and it's like, going back to set theory 101. But the point here is there's actually a different way to code pairs. There's something called a flat pairing function that I don't want to really talk about. You can actually do it pretty nicely. I think that the pairs I wanted to use were something like Quine-Rosser pairs or something. But the point is that you can, instead of using the usual Kuratowski pairs, you can use a pairing function so that actually functions from v alpha plus 1 to v alpha plus 1 are elements of v alpha plus 2. So you can get that to work for all ordinals above greater than or equal to omega. Of course, it can't work below, just because finite things aren't quite as nice as we would like. But you can have really simple, nice, definable pairing functions on all the v alpha plus 1s. And if we just change our notation so that a pair means that kind of pair, then everything works out much more nicely. But you can sort of ignore these comments and just don't think about pairing that much, or it can, if you think too much about what an ordered pair is, your head might explode. It certainly has happened to me. And if you look at the paper that I wrote with Farmer, you can tell we were thinking too much about what an ordered pair was, because it makes it very confusing. So I apologize for that. So ignore these comments and just pretend that functions from v alpha plus 1 to v alpha plus 1 are in v alpha plus 2. And it really makes very little difference. The comments are too technical to really matter. So, and they don't in the end. Or a good exercise is to try to make everything work perfectly formally and make sure that your head doesn't explode. Okay, so I wanted to tell you, why is it given a j from v lambda plus 3 to v lambda plus 3, it's elementary, is j definable over v lambda plus 3 from j restricted to v lambda plus 2. And the idea is to imitate the proof that we had in the v lambda plus 1 case. There, what you did is you defined j of x. So this is in the v lambda plus 1 case. It was equal to the union for alpha less than lambda of j of x intersect v alpha. And all you need here is j on v lambda, because x intersect v alpha is always an element of v alpha plus 1. So it's really heavily using that lambda as a limit ordinal, so that we have this nice hierarchy for v lambda. And we don't have a nice hierarchy for v lambda plus 2. So that's why this is sort of surprising fact. The fact that v lambda plus 2 has any kind of resemblance to v lambda is it's not obvious from the surface. Typically, you expect the successor levels of the cumulative hierarchy to all resemble each other. The limit levels all resemble each other. And instead, we're having this jumping up 2 every time thing. So when I first saw it, I thought, well, maybe that just means that these are inconsistent. But actually, the theory works pretty nicely with this periodicity. So we'll talk about that later as well. Not later today, but on the last lecture. So how do you do this? Why is it that if I give you j from v lambda plus 3 to v lambda plus 3, I can define it from its restriction to v lambda plus 2? Well, the first idea is there's a simple way to define an extension j of any embedding, of any embedding I from v lambda plus 2 to v lambda plus 2 to an embedding to act on functions from v lambda plus 1 into v lambda plus 2. So functions from v lambda plus 1 to v lambda plus 2. So these functions are really higher order objects. They're elements of v lambda plus 3, but they're sort of morally they're elements of v lambda plus 2. But things like a function in here, it isn't an element of v lambda plus 2, but it will act like one. Okay, so how do we do it? So if f is a function from v lambda plus 1 to v lambda plus 2, what you can do is encode f by an actual element of v lambda plus 2. this is the element, the relation that codes F. So R of F holds of all the X comma Y's such that Y is an element of F of X. Okay, so we have this function. It's taking in elements of V lambda plus 1, spitting out subsets of V lambda plus 1, but we're coding it by a single subset of V lambda, well, plus 1 times V lambda plus 1. So R sub F is contained in V lambda plus 1 times V lambda plus 1. And as I said, we're pretending that this is itself contained in V lambda plus 1. So if you want, you could use your flat pairing function to do everything, but you don't have to worry about it too much. Let's just pretend that pairs of elements in V lambda plus 1 are, again, elements of V lambda plus 1. You can make it true by changing what you mean by a pair. Everything still works just fine. Okay, so we can code any function from V lambda plus 1 into V lambda plus 2 by R sub F, which is in V lambda plus 2. And then we can define what we mean by I extended to F, which I'll write as I star of F. Well, this is just a function coded by I of R sub F. So I, remember, acted on V lambda plus 2. And so I can extend it. I mean, it just literally acts on R sub F. By elementarity, R sub F has to also code a function like this. So that's all you do. Okay. So what does that allow us to do? Well, we can sort of attempt to define an extension if we have an I from V lambda plus 2 to V lambda plus 2 to V lambda plus 3. So what you do now is if X is in V lambda plus 3, that means that X is a subset of V lambda plus 2. And so you can look at all of the small subsets of X, the ones that are the range of a function on V lambda plus 1, and move all of those. So what does that mean exactly? So we can define I plus. So I plus is going to be a map from V lambda plus 3 to V lambda plus 3. Define I plus of X to be equal to the union of the ranges of I star of F, such that F is in V, well, I can say X to the V lambda plus 1. So F is a function. Let's write it in a slightly less confusing way. So it's, sorry, I made a slight mistake. I meant to say the ranges, the union of the ranges of I star of F, where F is a function from V lambda plus 1 into X. So if we have a j from v lambda plus 3 to v lambda plus 3, like the one we're looking at, then and we take any x in v lambda plus 3, it's clear that j, if you take j restricted to v lambda plus 2, and you try to do this extension, the plus extension, and apply it to x, that has got to be a subset of the true j of x. Okay, let me write that again. So let me write the definition again of I plus. I plus of x is equal to the union, the range of I star of x, of f, as f ranges over all functions from v lambda plus 1 into x. So if so we've got j from v lambda plus 3 to v lambda plus 3, and we can look at I, the restriction of j to v lambda plus 2, and the question is, or what we want to prove, is that j is equal to I plus. So that tells us that j is definable from its restriction to v lambda plus 2. And in fact, if you think about it, this I plus operation is definable over v lambda plus 3. I mean, granting that j is actually an element of v lambda plus 3, which it is because of our careful choice of pairing function. So what I was saying before is that it's pretty easy to see that for any x in v lambda plus 3, I plus of x is always going to be contained in j of x. And that's because I plus of x is just the union of all these ranges. So if I have an f that goes from v lambda plus 1 into x, then I know that I star of f, which is because I is this restriction of a really elementary embedding, this is just equal to j of f. Right? I star just said, well, we'll code f into v lambda plus 2 and move over the code and then decode it as I star of f. And by elementarity, that has to be exactly what j is doing to f anyway, right? Because it's a first order fact about v lambda plus 3 to say that f is coded by this relation. And so that means that j of f must be coded by the place where j moved the relation. So I star of f is equal to j of f, and that means that j of f has to be a function from v lambda plus 1 into j of x. And that means that the range of I star of f has to be contained in j of x. So since I plus of x is this union, it's quite clear that I plus of x is contained in j of x. It's just the union of all these ranges, and each of these sets is contained in j of x. And if you take the union of a bunch of sets contained in j of x, it's certainly going to be contained in j of x. So this side of the equality is pretty easy. So in order to prove this, what we really need to do is show that for all x in v lambda plus 3, I star of x actually contains, I plus of x actually contains j of x. So that's the challenge. And the idea now, I mean, it's a sort of simple proof, but it's going to use something, it's going to use something about v lambda and v lambda plus 1 in a key way. So what we need to do is show that if we take some a in j of x, okay, and we need to show that a is in I plus of x. So that means that we need a to be in the range of I star of f for some f from v lambda plus 1 to x. And it's not that important that that f goes into x. So since this is the same as saying that a is in the range of some j of f, where f goes from v lambda plus 1 to x, since we know that j and I star are the same on these functions. So what's the issue here? It's not really this going into x. It's enough to show that a is in the range of j of f for some f from v lambda plus 1 into v lambda plus 2. And why? Well, we can just then make, let's say for some g. Because then we can define f from v lambda plus 1 to v lambda plus 2 to be f of x equals the empty set if g of x is not in x, and let's not use x's now. So f of u will be the empty set if g of u is not an x, and f of u will just be g of u. G of u is in x, or let's say not even the empty set, but just any fixed element of x. So x, little x0. So this gives us a function that goes into x now. And it will still have that a is in the range of j of f. Because a is in j of x, so j of f, so if since a is equal to j of g of some u, we'll have that a is equal to j of f of u, because by elementarity we'll be in this good case since a is in j of x. So this is sort of technical point, but you can try to convince yourself, if I haven't convinced you, that all we need to do is produce a g that acts on v lambda plus 1, such that our point a that we're interested in goes into the range of j of the function g. Okay, so that's what's going on. We're trying to show that j of x is always contained in I plus of x, and it reduces to this question of whether you can always get any a in v lambda plus 2 to be in the range of a function in the image of j. So that's what we need. So we need that every a in v lambda plus 2 is in the range of j of g for some g from v lambda plus 1 to v lambda plus 2. So this is actually the analog of the fact that an embedding, it's analogous to what we used implicitly for the v lambda to v lambda case, where we needed that any a in v lambda actually is in j of v alpha for some alpha less than lambda. So there's actually some property of v lambda plus 2 that's analogous to the property of v lambda that allows us to extend embeddings from v lambda to v lambda plus 1. This is just the fact that embeddings from v lambda to v lambda are cofinal. Every element of the range is an element of j of something in the domain. So the range of an embedding from v lambda to v lambda is always membership cofinal. That's what's going on here. And now this is analogous to it, but basically because the structures that we're working with aren't quite as simple, it takes a different form. So the claim is, in fact, yes, for any a in v lambda plus 2, there is a function from v lambda plus 1 to v lambda plus 2 such that a is in the range of j of g. So this is where j is our elementary embedding from v lambda plus 3 to v lambda plus 3. And in fact, another thing that you could write is for any a in v lambda plus 2 and any I, an embedding from v lambda plus 2 to itself, there's actually a g such that a is in the range of I star of g. So it doesn't really matter that whether I comes from an embedding from v lambda plus 3 to v lambda plus 3. So how do you do this? The idea is, so what is A? A is some subset of v lambda plus 1 because it's an element of v lambda plus 2. Okay, and you can say that A is always equal to the inverse image. Well, let's see. Yeah, so it's the inverse image of I restricted to v lambda plus 1 applied to I of A. That's just because the elements of I of A, just because a point U is in A if and only if I of U is in I of A. Okay. But another way to look at this is that A is equal to, well, we could restrict I even further down to v lambda And then we have this canonical extension of this up to v lambda plus 1. So let's write I. So if we have a k from v lambda to v lambda, this is now where we're starting to use our assumptions about embeddings. So if we have a k from v lambda to v lambda, I already said that you can always extend it to act v lambda plus 1 to v lambda plus 1. So A is also equal to this inverse image of I of A under the canonical extension of I to v lambda. So this is sort of how you jump back to in this proof. This is where the periodicity starts to show up. Okay. So what's our function g going to be? G is going to take in some k, and it's going to give me back, well, first let's extend k. So so G will take in k, and assuming k is actually an elementary embedding from v lambda to v lambda, we'll extend it to an embedding from v lambda plus 1 to v lambda plus 1, and then we'll take the inverse image under k of A. So G, well, it's a partial function, but let's not worry too much about that. It's a function from v lambda plus 1 to v lambda plus 2. It takes in some embedding from v lambda to v lambda, extends that embedding to v lambda plus 1, and then it takes the inverse image of our desired point A. And so that's just a bunch of elements of v lambda plus 1, which means it's a set. It's in v lambda. It's a subset of v lambda plus 1. So it's an element of v lambda plus 2. Okay, and the point is now that A is in the range of J of G. Why? Well, what's J of G applied to, well, sorry, it should be I star of G, because I'm working just with some embedding I. So what's I star of G applied to I restricted to v lambda? It's precisely, well, we take I restricted to v lambda, we lift it to v lambda plus 1, then we take the inverse image applied to I of A. So this is just I inverse image of I of A. I mean, it's just what I said before. It's just A. So A is in the range of I star of G, where G is a function of this form. So what's going on more generally? What we proved is that that lambda plus 2 has this property called the cofinal embedding property. So for any I from v epsilon plus 2 to v epsilon plus 2, I, so this, so you can define this property for any ordinal. It just says for any I from v epsilon plus 2 to v epsilon plus 2, and any A in v epsilon plus 2, there is a function from v epsilon plus 1 to v epsilon plus 2 such that a is in the range of I star of the function. So this is the right notion of a cofinal embedding at the level of a successor ordinal. And the fact that we proved, well, we have to, it's sort of an, what we proved was that v lambda plus 2 to v lambda plus 2 embeddings have this cofinality property. And what we needed for it was the fact that every embedding from v epsilon to v epsilon could, well, that every embedding from v epsilon plus 1 to v epsilon plus 1 was the canonical lifting of an embedding from v epsilon to v epsilon. Okay, so we showed that, but now we know that that's true at, say, v lambda plus 2. And so inductively, we can show, right, we showed that, so we needed this canonical extension property at epsilon plus 3. So for any I from v epsilon plus 3 to v epsilon plus 3, I of, for all x, I of x is just equal to the union of all the i's, the ranges of I star of f, where f is a function from v epsilon plus 1 into x. And what we showed is that if we have the canonical extension property at, well, let's say this at epsilon plus, well, our proof is basically giving us, we can extend using these two properties. We can generalize the proof. They'll show that if the cofinal embedding property holds, at epsilon plus 2, then the canonical extension property holds at epsilon plus 3. So that's what we just showed. That was how we showed that I plus of x actually contains, or j plus of x actually contains j of x. That's what we needed this cofinal embedding property for. Okay, but the way we got the cofinal embedding property was using the canonical extension properties 2 down. Although the canonical extension property for limit ordinals is stated in a slightly different way. But okay, so now if we have the canonical extension property at at epsilon plus 3, then the cofinal embedding property actually holds. So this is something new, I guess, that I hadn't said before, at epsilon plus 4. But it's just the same proof that I just did that the cofinal embedding property holds at epsilon plus 2. It uses the fact that you can extend embeddings of v epsilon to v epsilon plus 1. So now I'm just doing the same thing at epsilon plus 4, using that you can extend embeddings from v epsilon plus 2 to v epsilon plus 3, which is what we just proved. So from the cofinal embedding property, you get the canonical extension property of the next ordinal. from the canonical extension property, the next ordinal, you get the cofinal embedding property again at the next ordinal. So that's what's driving this periodicity. So by induction, so we start at v lambda plus 2 and v lambda plus 3. By induction, we ultimately get the theorem. The cofinal embedding property at every even ordinal, and the canonical extension property at every odd ordinal. So I guess because of the way the cofinal embedding property is stated, it really only makes sense to say that we have the cofinal embedding property at every even successor ordinal. And the canonical extension property is stated in such a way that we only have it at every odd ordinal that's at least 3 more than a limit ordinal. There's another version of the cofinal embedding property that holds at limit ordinals, and a version of the canonical extension property that holds at successor ordinals. It's basically what I told you when we started out about how you can extend from v lambda to v lambda to v lambda plus 1. But it's the statement is slightly different. You can make the statements look exactly the same everywhere, and that's what we did in the paper. But I actually think that it's a little bit more confusing. So you can look at the paper if you want, but here I think it's better to actually just split out the limit case, because otherwise it's just, for me, it's harder to think about. Okay, so in any case, the point is you propagate these cofinal embedding properties and canonical extension properties, and each one gives you the next property at the next ordinal, and that's why it alternates. Okay, so this does get us the theorem that if J goes from V alpha to V alpha, well, V lambda plus n to V lambda plus n, where lambda is a limit ordinal and n is odd, then J is definable from its restriction to V lambda plus n minus 1. And to finish off the theorem, what we really need to do is show that conversely, if n is even, J is not definable. So the idea here actually is to prove a more general fact, which is, so this proof of this undefinability theorem, Farmer, Schlutzenberg, and I proved in 2 different ways. I'm going to do his proof because it's better. Sometimes you have to admit that even to yourself. Okay, it's so the theorem that he proved was if you have any J from V alpha to V alpha, it's elementary, and you have a parameter P that's in the range of, okay, so let's do this as a successor ordinal. It's in the range of J star of F for some F from V alpha to V alpha plus 1. Then J is not definable from F. From P. Okay, so what's going on here? Why does this finish the theorem? Well, we said that the even ordinals have this cofinal embedding property. So if we look at this as, so in the case, if epsilon is even and J is an elementary embedding from V epsilon plus 2 to V epsilon plus 2, then for any P in V epsilon plus 2, J is not definable from P. And the reason is, for any such P, the cofinal embedding property tells us that there is some function f from V epsilon plus 1 to V epsilon plus 2, such that P is in the range of J star of f. So by the cofinal embedding property, we have this P has this form, and so we can use Farmer's more general theorem to conclude that, that J is not definable from the parameter P, just for any parameter in V epsilon plus 2. But even in the odd case, this theorem is true, and it shows us that odd ordinals do not have the cofinal embedding property. So these two properties that we were propagating, they really, the odd ordinals don't have the cofinal embedding property. The even ordinals do not have the canonical extension property. So there really are these very distinctive properties that are propagating through all the ordinals. So before I get started with Farmer's proof, let me let's take another 5-minute break. It's just I feel like maybe it's so hard to tell on Zoom, but I'm a little worried that I'm exhausting you with details.
Okay. So maybe we can take 15 minutes.
Oh yeah, that's fine. I think after 15 minutes, I'll still have enough time to finish this proof.
Okay, okay.
Yeah. Okay, so remember where we were. We had proved that even ordinals have this cofinal embedding property. So the fact that we proved is if epsilon is even and you have an elementary embedding J from V epsilon plus 2 to V epsilon plus 2, then every element A of V epsilon plus 2 belongs to the range of J star of f for some function f from V epsilon plus 1 to V epsilon plus 2. This is what I call the cofinal embedding property. So every A is in the image of a small set is really what this is saying. It's in the image of a small subset of V epsilon plus 2. Okay. And then the theorem of that Farmer proved was that if alpha is any ordinal and J is an elementary embedding from V alpha plus 1 to V alpha plus 1, and P is an element of V alpha plus 1 that's in the range of J star of f for some f from V alpha to V alpha plus 1, then J is not definable from P. Okay, so this shows the theorem we're trying to prove, which is that embeddings from even levels of the cumulative hierarchy to themselves are not definable. So there's a slightly different thing that you have to do for limit ordinals, but it's actually essentially the same proof. It's just actually easier. So the issue, so the proof of his theorem, well, the idea is to imitate the proof of Suzuki's theorem. So let me explain how that goes and how it goes wrong. So what you say is, okay, so suppose towards a contradiction, J is definable from some P. So we have, sorry, I should just say J is from V alpha plus 1 to V alpha plus 1. And it's definable from some P, which belongs to the range of J star of F for some F going from V alpha to V alpha plus 1. Okay, so that means that we have J of A is equal to B if and only if phi holds, let's say in V alpha plus 1, phi holds of A, B, and the parameter P. That's what it means to be definable. So for some fixed formula, phi, in the language of set theory. So what can you try to do? Well, for each Q, you can try to define JQ function from V alpha plus 1 to V alpha plus 1 by setting JQ of A equal to the unique B, if it exists, such that phi holds of such that V alpha plus 1 satisfies that phi holds of A, B, and Q. So we're trying to get rid of the dependence on the parameter. And let me explain why you really want to get rid of the dependence on the parameter. It's very obvious that there cannot be an embedding, an elementary embedding that's non-trivial and definable without parameters. And the reason is that its critical point would be definable, but then its critical point wouldn't be able to move. And what you're trying to do here, which I should have explained when I explained Suzuki's proof, but because it was very early in the morning and you have to forgive me. But because it was early, I forgot to say this. The point of the whole proof is to get rid of the parameters and be able to get the same contradiction. So that's why we start looking at a J sub Q that's defined from an arbitrary parameter. The idea is that we're going to look at all the parameters and minimize the critical points, and that will help us get to a contradiction. So say Q is bad if one, JQ defines a function, two, JQ defines an elementary embedding, okay, so that sort of goes farther than one. And 3, there is some f, or let's call it g, since I already used f, from v alpha to v alpha plus 1, such that q is in the range of jq star of g. Okay, so these are the parameters that, using this formula phi that we fixed, give rise to a counterexample to our theorem. And so what you'd like to do is, as in Suzuki's proof, fix a bad parameter r in v alpha plus 1, such that the critical point kappa of j sub r is as small as possible. Okay, and now also fix g from v alpha to v alpha plus 1, such that r is in j sub r, or in the range of j sub r star of g. Okay. So if you look at the set of all critical points j sub u, such that u is in the range of j star, j sub r star of g, and u is bad, well, this is going to be, it's greater than, or sorry, we're going to look at the minimum element of this. Why is kappa less than or equal to the minimum element of this? Well, kappa is the minimal critical point of a bad parameter, so it has to be below all of these. But also kappa is in this set because r is supposed to be in the range of jr of g. So it follows that kappa is actually equal to the minimum element of this set. And then the contradiction is supposed to come from the fact that, therefore, if we look at the minimum kappa bar, the minimum element of the critical points of j sub u's, such that u is in the range of g, the range of g, and u is bad, well, then it should be that j sub r kappa bar is equal to kappa. So that would tell us that kappa is in the range of j sub r, but that's impossible because kappa was equal to the critical point of j sub r. So that should be a contradiction, but there is a tiny, very annoying problem. And for this reason, for this problem caused me to, spend another couple of days on this, and I have a completely different proof of this undefinability fact. That it actually is it uses some other techniques, some ultra filter techniques. But Farmer works on fine structure, where when a tiny annoying fact comes up, what you do is you fix it. So he came up with a nice idea that gets rid of this tiny annoying problem. But first, let me tell you what the annoying problem is. The problem is this concept, U is bad, is not first order over V alpha plus 1. And so the problem isn't these G's, which remember they go from V alpha to V alpha plus 1, so they're technically not elements of V alpha plus 1. That's not actually a very big deal. But so these are fine because remember they're all coded by relations on V alpha. So they're all essentially elements of V alpha plus 1, so we can talk about them. The problem now is what was the definition of bad? So remember, a parameter was bad if it defines a function that's an elementary embedding. Okay, that's the problem. And there's this condition about the existence of this G. So this 3 is first order over V alpha plus 1 because you can quantify instead of over all these G's, you quantify over the relations that code G. And that's just fine. Defining a function, that's totally fine as well, but defining an elementary embedding is a problem. Because saying that something is elementary depends on the whole satisfaction predicate of V alpha plus 1. And remember in the Suzuki theorem, we got rid of this problem. And the way to get rid of it was to say, well, elementary is equivalent to being sigma 0 elementary and cofinal. And in the case that we're in, the embeddings are actually sort of similar to cofinal embeddings, right? For the even case, they have the cofinal embedding property, but it doesn't even help here because that whole theorem about cofinal embeddings being fully elementary, it heavily uses the fact that the domain of the embedding is a model of ZF. And we're working with V alpha plus 1. I mean, V alpha plus 1 doesn't even satisfy the pairing axiom, let alone, so it's you're actually sort of closer to satisfying ZF than you might think in these things. Really what you would need here is to satisfy the axiom of collection in V alpha plus 1. Well, okay, that doesn't really happen, but something like it might happen. But in the end, to show this analog of the sigma 0 of sigma 0 implying fully elementary would require something like the axiom of choice. So you really are in trouble here, or it seems like it. And it's such an annoying issue because the proof seems like it should work. So, okay, what do you actually do? So this is it's a nice trick that Farmer came up with. So what you do instead is you define a new notion. Instead of bad, you look at the notion of an n bad parameter. So for each n less than omega, a parameter q is n bad if one, this formula phi with the parameter q defines sigma n elementary embedding from V alpha plus 1 to V alpha plus 1. And 2, the same other badness condition that q is in the range of this embedding applied to some g, or g in let me think, for g a function from V alpha to V alpha plus 1. Okay, so this is our new concept, and the nice thing about it is it's first order. Sigma n elementary just talks about the sigma n satisfaction relation, and you can define that by a sigma n plus 1 formula. Do better than that as well, but okay. So it's first order statement. So it's going to be preserved by all the elementary embeddings. So now, what do you do? So we still have the concept of a bad parameter. So we fix our bad parameter. So J sub R is fully elementary from V alpha plus 1 to V alpha plus 1. And we still want that the critical point so JR is elementary, and R is in the range of J sub R star of G, or some G, V alpha to V alpha plus 1. So kappa is the critical. Sorry to write that all again. Okay, so let's see. What I want to say is, we looked at this before at this minimum point, the min of all over all critical points of J sub U for U bad parameter. And U, let's see. In the range of J sub R star of G. So, and the point was that this was kappa, and I wanted to show that that means that kappa is in the range of J sub R, because look, this doesn't look like it uses any parameters except for J R of G, which is in the range. So it's very close, except that bad parameter was too complicated. So what we'll do is we let D sub n be equal to the, let me be a little careful here. Let D sub n be the set of all A in the domain of G, such that G of A is n bad. Okay. So the point is now that if we want to look at the set of all critical points of J sub U, such that U is n bad and U is in the range of J sub R star of G, that's the same as looking at the set of all critical points of J sub U, such that U is of the form J star sub R of G of A for some A in J sub R star of D sub n. Okay. So so this is let's call that S sub n, this set of critical points. And the set we're interested in, S, is equal to the set of critical points of J sub U, such that U is bad, so it's in well, okay. So what I really want is to look at the set of J sub U's that U is bad and U is in this range. But what that's equal to the set of crit J sub U's such that U is equal to JR of G of A for some A that's in the intersection of all of these sets. All right. So the point here is I'm still just trying to get the original set that we were dealing with to be definable from some parameters in the range of J. Sorry, and this is just J R. So all I really need now is that this set is in the range of J. So let's see. I want to show, in fact, that this intersection of the JR of D sub n's for n less than omega is just equal to J sub R of the intersection of the D sub n's. Well, that's actually just true. These D sub n's are elements of V alpha plus 1. So the whole sequence of D sub n's is essentially an element of V alpha plus 1. Again, this is because V alpha plus 1 is morally closed under V alpha sequences. So it's the same way we get this JR star. And so, okay, so this is the same as the set of all A's that are in JR of the intersection of the D sub n's. Okay, so finally, I have a first order property that I can use to get a contradiction. So the point was, we know that kappa is equal to the minimum critical point of one of these J sub U's for U, a bad parameter, and U in the range of J sub R star of the function G. And we said that that set that we were looking at, the same as the minimum critical point of JU, such that U has the form JR star of G of A for A in J sub R of the intersection for n less than omega of these sets D sub n. Okay, and all of this stuff is first order with parameters in V alpha plus 1. So here there's some minor glitch because G isn't technically in V alpha plus 1. So, but this is, remember there's this relation that codes G. So we could say R sub G. So U is actually equal, so we could say something about J of R sub G instead of saying U is equal to this, but it would be a little complicated. But anyway, it's all of these things can be written using just parameters that are in the range of J sub R, so we can pull it all back. So we have that there must be an ordinal kappa bar. We can let kappa bar be the minimum ordinal that's of the form a critical point of J sub U for some U of the form G of A, where A is an intersection of the D sub n's for n less than omega. And elementarity now literally tells you that J sub r of kappa bar is equal to kappa. And that is actually a contradiction. Okay, so the moral of the story here is that sometimes if there's a little problem in your proof, there's also a small solution. Just something that I learned from this proof. And again, that this is something that happens all over the place in set theory. If you have a proof that seems to be about very large objects, like Suzuki's proof that there's no definable J from V to V, often you can sort of localize it to tell you much more information about small things. Okay. Yeah, so that's all I have to say, I guess, for the day, but it does, I guess I should finally restate it, what we've proved. The theorem is just if J goes from V alpha or V nu to V nu, then J is definable over V nu. From parameters, if nu is odd. So actually there's one case that we didn't do, so I'll put this on the homework, but the case where nu is a limit ordinal, sort of the most basic case. I didn't specifically do that case, but you'll see it's very similar to what we just did with the little version of Suzuki's theorem. Okay, thank you.
Okay, thank you. And is there any questions on the problem? Anyone has questions? No. If no questions, that's all of today. Thank you.
Okay, great.
Thank you.